Can you check on YouTube, please? Yes, it works.
Yes, I see that there's a live stream happening at the moment independently. So
Okay,
this is good. Good.
We're back in business.
Back in business. Thanks, Liviu.
Okay, bye.
Okay, bye. All right, so thank you everybody for bearing with us as we get everything set up for this week's monsoon seminar. This week, we are joined by Dr. Stefanie Tofelde from the University of Potsdam. And so again, just housekeeping as usual, please type your questions into the chat, and at the end, we'll read them out, and then you can either ask them live or then we can just kind of read them out for you. I'll send a couple of other little messages in the chat as well regarding meeting potentially in person for an upcoming international meeting, like AGU, for example, or for EGU. Details will be in that, and Peter has sent out another email. And then, of course, as usual, if you want to join the mailing list for this, send me an email, Liviu an email, or Peter an email, and we shall add you. So again, without further ado, we want to thank Stefanie Tofelde for joining us. And if you would please start off, Steffi, we'll learn about the South American summer monsoon.
Yeah, thank you very much, Tara, for the introduction and also for the invitation to speak here at the Monsoon Seminar Series. And yeah, today I'm going to talk about the South American summer monsoon and its impact on sediment transport in the southern central Andes. But before I start doing this, I would like to take a moment to acknowledge my collaborators who have either helped to have help with the work that I'm presenting tonight, that I was doing myself, who have led some of the work that I'm going to show tonight. So the seminar is going to be subdivided into 4 parts. And because the majority of previous seminars have been focusing on the Asian monsoon, I will give an introduction to the South American monsoon system first, and then talk a bit more in detail about the study region, northwestern Argentina, and what we actually know about the monsoon history of this region. Then in the second part, I will move more to my own work, and I will be talking about how variability in climate has impacted sediment transport in rivers and form river terraces, and how we potentially can use those river terraces to reconstruct hydrological conditions of the past. But let's get started and talk about the South American monsoon system first. What you can see here is a topographic map of the Andes on the left and the distribution of mean annual precipitation on the right. So the Andes are about 7,000 kilometer long mountain chain oriented more or less north-south. And the highest peaks of the Andes are even higher than 6,000 meters. So because of this north-south orientation and the high elevation, the Andes are quite effective orographic barrier for major winds. So the combination of the direction of wind systems in South America and the Andes acting as orographic barrier results in this very characteristic pattern of rainfall or precipitation distribution in South America. So here on north of about 30 or 32 degrees, we have very high rainfall rates on the eastern side of the Andes. In this region, more than 4 meters per year, while we have very low rates on the western side of the Andes. So the Atacama Desert only receives about 20 millimeters of rainfall per year. And this rainfall pattern is inverted about south of about 30 or 32 degrees. But for today, I'm only going to focus on this northern part here. So this figure shows the distribution of mean annual precipitation. But actually the precipitation in South America is highly seasonal. And this can be seen in these 2 maps. On the left, we have the distribution of rainfall during the austral winter, so during the 3 months of June, July, and August. And on the right, we have the distribution of rainfall during the austral summer, December, January, February. And what you can see here is that during the austral winter, most precipitation is focused in a quite restricted area here in the northern part along the intertropical convergence zone. But this pattern looks very different in summer. So during the summer, this is when the monsoon develops. You can see that this region of high precipitation is moving further to the south, and it brings high precipitation rates into the central Andes. So during the monsoon phase, the IETZZ is deflected to the south. And as a consequence of this, moisture from the tropical Atlantic can be transported by easterly trade winds across the Amazon basin until they hit the Andes, acting as an orographic barrier. And that's why we have these high rainfall rates here along the eastern margin of the Andes. However, not all clouds just rain out here. A fraction of these moist air masses are actually deflected to the south, and they are transported by the so-called South American low-level jet along the eastern margin of the Andes. And basically, every time they hit the high Andes, they rain out here. So the impact of the Andes acting as an orographic barrier on the rainfall pattern has been investigated in more detail by Bodo Buchhagen and Manfred Strecker. And they have analyzed the distribution of mountain elevation, so here from the SRTM data, and the distribution of rainfall from the TRMM satellite data along or across more than 100 swaths across the Andes. And 4 exemplary swaths are shown here on the right. So they are located at these sites where we have these thick white lines. One is here, one from the central part, and then down here. And when we take a look at these cross sections or swaths, the black line in each of these profiles shows the distribution of elevation, so the SRTM derived elevation, and the blue line shows the distribution of rainfall. So the numbers on the y-axis, they correspond either to elevation in kilometers or in rainfall given in meters per year. And on the x-axis is just the distance across the Andes. And we can see in the northern part, the elevation of the Andes is not so high yet. So we have some rainfall on the eastern side, but actually the majority of rain on the western side. Yeah, this can also be seen here where this northernmost swath is located. It's a bit hidden under this legend. But the further we move to the south along the Andes, going to swath 49 or 74 or 90, we can see that the Andes get higher and they act more and more like an orographic barrier. So here we have most of the rainfall on the eastern side of the Andes when these low-level jets actually hit the easternmost ranges. And there's very, very little rainfall on the Altiplano and Puna Plateau in the central part of the Andes. So that is roughly today's pattern of the South American monsoon and how it impacts the rainfall. But the question is now about how did it change through time? How did the monsoon behave in the past? And for that, we're going to take a look at a couple of paleoclimate records. The first one is from the Botovera cave located in southeastern Brazil. And today, this region receives rainfall during the monsoon phase, and it's rain that is, it's water that has been traveling across the Amazon basin, being transported down here by the low-level jet, and rains out. And in this Botovera cave, Wang et al. Have measured oxygen isotope or the oxygen isotope composition on calcite stalagmites. So they had a sample that was about 25 centimeters long, which corresponds to roughly 90,000 years. And then along the stalagmite, they have measured the oxygen isotope composition, which is shown here by this blue curve. And the oxygen isotope composition varies with the amount and the source of rainfall. So during strong monsoon, there's lots of moisture is recycled over the Amazon basin before it gets transported to southeastern Brazil. And this leads to a depletion in the isotopic composition. So we have to be a bit careful here. The y-axis is actually inverted. So a strong monsoon, meaning high rainfall in southeastern Brazil, means very depleted values. So it's these high parts in this blue curve, these wet conditions. Then the other curve that we see, that's the gray curve. This shows the summer insolation at this site. And we can see that the summer insolation in the tropics has changed in phase with about 20 kiloyear precessional cycle. And what this shows is that strong monsoon phases apparently occurred in phase with insolation maxima, while weaker monsoon phases occurred during insolation minima. So this is the situation here at the coast, but we're now particularly interested in the Andes, and therefore we're going to take a look at paleoclimate records from the Altiplano Plateau. And on the Altiplano Plateau, which is shown here in this very little map, there are today several lakes, freshwater lakes and salt lakes. For example, here we have the Lake Titicaca, and a little bit further to the south, we have a salt lake called Salar de Uyuni. And in this salar, Baker et al. Have measured the gamma radiation in a drill hole that represents about 50,000 years. And the gamma radiation is a proxy for effective moisture. And the idea is that during wetter conditions, there's more lacustrine muds deposited, and lacustrine muds have a higher gamma radiation, while during drier conditions, there are more salts deposited, and salts have a lower gamma radiation. So the value of gamma radiation shown here on the y-axis basically indicates wet phases for high gamma radiation, and lower gamma radiation indicate dry phases. And again, you can see the same picture here, that wetter phases on the Altiplano Plateau obviously correspond to insolation maxima, while drier phases correspond to insolation minima. And these different records are now just summarized here again, all overlain. The black one is the oxygen isotope record from the Botuara Cave, here from southeastern Brazil. The greenish curve is the gamma radiation record from the Salar de Uyuni from the Altiplano Plateau. And then the red dashed line is the insolation curve. So during the last 50,000 years, we had two phases of monsoon intensification during insolation maxima, one at about 40 to 45,000 years, and another one here at about 20 to 25,000 years. And at both of these times, there's a lot more evidence for large freshwater lakes that formed on the Altiplano and Puna Plateau that I just haven't shown here yet. Okay, but those changes in moisture, they did not only impact the extent and distribution of lakes or the oxygen isotope composition in stalagmites, but it has also impacted the distribution of glaciers. And yeah, today the Andes are central Andes are relatively dry. Most regions are actually unglaciated due to the warm and dry climate. But in the past, during the last several tens of thousands of years, the Andes have experienced glacial advances during cooler and wetter times. And Mitch Darcy has actually compiled and recalculated all moraine ages between about 5 degrees and 30 degrees south, and then binned them in 5-degree bins. So these green shading areas that we see here show times of glacial advances as a function of latitude. And what we can see is that during these two phases of insolation maxima, so when the monsoon has been intensified, these also correspond to times of glacial growth and the formation of moraines, also here. But in addition, we see some further moraines, some younger ones that don't directly correspond to the insolation maxima anymore. In particular, we see moraines during the Heinrich Stadia 1 and the Younger Dryas. So apparently, the monsoon intensity is not only controlled by insolation-driven cycles, but also by millennial scale climate events like the Younger Dryas or Heinrich Stadia hydrostadials. Okay, so now we have some idea about how the monsoon intensity changed through the last 50 or so thousand years. But yeah, things get a bit more complicated when we think about longer timescales, because there are just less proxies available, especially not moraines, because they often get destroyed during later glacial advances. But when we go back to the Altiplano Plateau, we do have lake records that date back further in time. And the one that dates back furthest in time is a lake core from Lake Titicaca that covers about 350,000 years. And from this lake core, Baker and Fritz, or in this lake core, Baker and Fritz have measured the concentration of saline diatoms or calcium carbonate. And both of these are a proxy for dry conditions. So whenever we have a high concentration in saline diatoms or a high concentration of salts that have precipitated, this is an indication of very dry conditions on the plateau. So therefore, these gray bars here now represent times of very arid conditions on the plateau. And when we have little concentration of saline diatoms or salt precipitation, this is, so the white spaces in between, these are the times where it has been wetter on the plateau. And if we now compare this to a global paleoclimate record, in this case, it's the Vostok ice core, we can see that the dry phases on the Altiplano Plateau correspond to global interglacial phases quite consistently, while the wetter phases, the white spaces in between, correspond to transition into glacial phases or the glacial phases. So here, this is the LGM, for example. Okay, to sum this up, what we know is that the interplay of the Andes acting as an orographic barrier and the monsoon-related winds today largely control the rainfall distribution in this northern part of South America. But from different proxy records, we could see that the intensity of the South American summer monsoon has varied through time. On the one hand, with orbitally driven insolation cycles, but also with millennial scale climate events like the Younger Dryas or hydrostadials. And also what we could see, which I maybe didn't explain so well, and I might quickly jump back, is that the moraines and the glacial extent are not the same everywhere, but we have a trend along latitudes. So in the northern parts, let's say between 5 and 15 degrees, glaciers have been formed at many times in the past. But the more we move to the south, in this region, glaciers only formed at very particular times. So when the monsoon has been particularly wet and has transported wet air down here to this lower boundary of where the low-level jet actually can transport moisture. Okay, so therefore, particularly the southern region between 25 and 30 degrees, that seems to be quite sensitive and only receives enough moisture to grow glaciers during particularly wet times. Therefore, this region is of particular interest. And next, we're going to take a closer look, especially at this region, our study site in northwestern Argentina. So we are located roughly between 22 or 23 degrees and 30 degrees south. So this is the region indicated here by this red box, all more or less in northwestern Argentina. So on the western side, we have the high elevated Puna Plateau, and on the east, or in the east, we have the low elevated foreland area. And these two areas are connected by intermontane basins, shown here more or less in green. Here on the right, you now see the mean annual rainfall distribution in northwestern Argentina. And as explained before, the majority of the rain that falls here is transported here by the low-level jet coming from the Amazon basin, transported southwards, and every time the winds hit the easternmost ranges, they just rain off. So therefore, we have a very strong spatial east-west gradient in rainfall. We have high rainfall rates in the eastern part along the easternmost ranges, rates of more than 2 meters per year, but we have very little rainfall in the internal part on the Puna Plateau, where rates are about 200 millimeters per year. In addition to the spatial gradient, we also have a seasonal variability. So most of the rainfall is falling during the monsoon season. It's about 80% between November and February. And this strong gradient in rainfall that we see here can also be seen in the distribution of vegetation. I just brought 2 images to give you an idea. Here in the foreland area where rainfall rates are high, we have a dense rainforest, while on the Puna Plateau, where rainfall rates are on the order of 200 millimeters per year, vegetation is very sparse. We mainly find some shrubs and bushes. But this gradient in rainfall does not only impact the vegetation, it also impacts the distribution of erosion rates. And what you can see here is a study by Bodo Burghagen and Manfred Strecker. And they have shown the distribution of rainfall, which are the colors in the background. So here the low rates on the plateau and the high rainfall rates in the foreland. And they compared this to the distribution of erosion rates, which have been measured from cosmogenic 10 beryllium. And we can see that on the Puna Plateau, or in these intermontane basins where rainfall rates are low, also the erosion rates are fairly low. So the erosion rates are represented by the size of the circles, I should say. While in the foreland area, rainfall rates are higher and erosion rates are also higher. So this is today's distribution of rainfall as we see it in this region. But the question also here is, how did this change through time? In the study site, so in northwestern Argentina, there are no major glaciers today, but we see moraines that indicate there has been glaciation in the past. And in particular, in our study site, there are 3 regions indicated by those yellow stars where moraines have been dated. And the ages that we find, they fall here into the 40 to 45 year wet phase, 20 to 25 kilo year wet phase, and into the younger dryas. So apparently during the 2 installation maxima and during the younger dryas, this region has been wet enough to form glaciers. But the question is now, how much wetter was it actually compared to today? And there are a few studies who have looked at quantitative reconstruction of paleohydrology. And one of the studies I would like to show here, this is work by Jürgen May. And what Jürgen has done is he has combined those dated moraines with dated lakes or remnants of dated lakes. And then he coupled a model on the paleoglacial extent with a model on paleo lakes. And he was looking for which combination of changes in temperature and changes in precipitation can best explain the extent of glaciers and lakes in the past. He has done this for 3 points in time, the younger dryas, the Heinrich Stadial 1, and the LGM. So he was restricted to those times for which moraines and lakes are available. We can see on the x-axis, this is the change in temperature compared to today. And on the y-axis, we have the change in precipitation compared to today. Now we can see for the younger dryas and the Heinrich Stadial 1 that it must have been on the order of, let's say, 2 to 3 degrees colder and about 10 to 20% wetter in order to grow these glaciers and to form such lakes. So as I said, there are a few more studies that did some quantitative paleohydrological reconstructions, but all of these studies are limited to the last few tens of thousands of years because they are restricted to the availability of either moraines or lakes. However, from other work, we know that the monsoon system and moisture-bearing winds that have been transported in this region have existed for several millions of years. And one of this study from which we know that it was work that was led by Alexander Roman, and he has investigated a more than 2 kilometer long stratigraphic profile in the Angastaco Basin. So the location of the Angastaco Basin is shown here in this little black triangle at about 25 degrees south. And today, the Angastaco Basin is an intermontane basin that is fairly dry, but is still externally drained. So to the west, we have the Puna Plateau, but to the east, we today have mountain ranges that are basically high enough to prevent the moisture to actually reach into the Angastaco Basin. Most of the moisture of the rainout happens on the eastern flank of these eastern ranges. But what Alexander has done was measuring hydrogen isotopes in lipid biomarkers in N alkanes and oxygen isotopes in soil carbonates along this more than 2 kilometer long section, which represents roughly 8 million years. And both of these proxies, or both of these parameters, are actually a proxy for moisture or precipitation. So lower values indicate wetter conditions and higher values indicate drier conditions. And both of these data sets show more or less at the same time a shift to wetter conditions sometime since about 8 to 7.5 million years ago. And this shift is interpreted as the onset of the low-level jet. So by that time, these eastern ranges were high enough and moisture transported down there by the low-level jet, or moisture reached down there so that it actually could rain off, and this region became wetter. Then a little bit later, at about 6.5 or 6 million years ago, this region became drier again, so it experienced some aridification. And this has been related to the uplift of those eastern ranges that eventually prevented the clouds from going over and reaching the basin. And a very similar pattern in the evolution of intermontane basins has been shown by work from Heiko Pingel. And what Heiko has been doing was also measuring hydrogen isotopes, but this time in volcanic glasses, so in glasses that have been or that are incorporated in volcanic ashes and incorporated in sedimentary fields. And the same here, lower values indicate wetter conditions and higher values indicate drier conditions. And the study site that he was working in that's the Toro Basin. I marked this here by this red box, so it's just a little bit north of the Angastaco Basin. And we see a quite similar history. So sometime between 8 and 6 million years ago, there's a phase of wettening. And Heiko explains this by tectonic uplift of these ranges. So eventually these western ranges became high enough to act as an orographic barrier, and they caused rain out from moisture that was transported down here by low-level jets. So this is the situation since about 7 million years ago. However, then we also here have another phase of aridification. It's a lot later. It's only at about 800,000 years ago. And also here, this aridification has been explained by the uplift of these eastern ranges that are eventually so high that they act as an orographic barrier and prevent the moisture from crossing the range and reaching the Toro Basin. So since about 800,000 years ago, the Toro Basin also has experienced some major aridification. Okay, to sum up what we learned about the study area. On millennial timescales, there are some quantitative reconstructions of wetter phases during the Younger Dryas, during the Heinrich Stadials and the LGM, but they are all restricted to the last few tens of thousands of years. However, we know from isotope studies that the monsoon has impacted this region for the last several million years, so at least since about 7.6 million years ago. And later, acidification of individual intermontane basins has been explained by orographic uplift. But one of the outstanding questions that we still have is, how can we quantify past hydrological conditions prior to the last 20,000 years? And this brings me now a bit more to my own work. And the idea here is that changes in climate do not only form glaciers or lakes, but they also impact erosion rates, as we have seen by the work from Bodo Burghagen and Manfred Strecker. And therefore, this also, changes in climate should also impact sediment transport and the evolution of river systems. So what you see here is a very idealized longitudinal river profile that shows elevation over distance. It has this typical concave up shape. And what we know is that the slope of the river, or the channel gradient, is a function of upstream sediment supply, known as QS, relative to upstream water discharge, QW. And that means if we have changes in sediment supply or water discharge, for example, due to changes in climate, this should impact the channel gradient. For example, more water discharge or less sediment supply should both result in a lower slope. And this will actually cause river incision into formerly deposited sediments. However, we have to be a bit careful because changes in riverbed elevation are not always due to changes in upstream sediment supply or water discharge. They can also be the consequence of downstream perturbations. For example, when the elevation of the base level changes, here we have a base level drop. This can also initiate an upstream migrating nig wave and change elevations in the channel bed. So that we do have massive changes in channel bed elevations in northwestern Argentina becomes obvious when we go to the field. There's a few photos here. They are from the location marked by these white stars. So these two stars represent two intermontane basins. And in both of these basins, we can actually observe drastic sediment deposition or river aggradation during the last 30 years. So in this case, this is an example from the Humahuaca Basin. The river has deposited so much sediment that it has filled the entire space between the initial channel bed and this train bridge. So as a consequence, this whole train line had to be abandoned sometime in the 90s already. Here's another example from the Toro Basin. Here we see some trees. And this area used to be a nice picnic area for families on the side of the river. But by now, the river has aggraded so much that it has just incorporated this region into the active channel belt. In other sites, there's also some evidence that there have been phases of river incision. For example, here, where the river has later on incised into previously deposited fluvial sediments. So changes in channel bed elevation do happen, but if we want to use them in order to reconstruct some paleoclimate, they need to be preserved. And this is where the terraces come into play. Because those fluvial terraces, they form due to changes in channel bed elevation, so due to alternating phases of river aggradation and river incision. And those flat surfaces that you see here, the terrace surfaces, they are the former floodplains or channel beds that have been abandoned when the river starts to incise. So therefore, these terraces are quite interesting because they preserve the geometry of channels in the past, channels of the past, and at the same time, they also preserve sediments of the past. To give you a bit of a better idea of how this looks like in the field, I have a few photos here. And you can see these terraces are very obvious in the field. They are quite pronounced surfaces. When you stand on top of those surfaces, they're extremely flat, fairly extensive. And when we dig some pits, we can also see that this is nicely fluvially deposited sediments. We find terrace sequences in many of these intermontane basins, but the ones I'd like to talk about today is the terrace sequence in the Quebrada del Toro, indicated here by this red star. It's the study site that I was talking about before, where Heiko Pingel did his work on the isotopes in the volcanic glasses. So the basin that has experienced some aridification in the last 800,000 years. So as a first step, if we want to use those terraces for any kind of reconstruction, we need to get a terrace chronology. And in order to date these terraces, we combined several dating techniques. So we used cosmogenic depth profiles that we sampled in pits dug on the terrace surfaces in order to get the terrace surface ages, or the time when these terrace surfaces have been abandoned, which are the times when the river starts to incise into its former deposited sediments. And then we have a couple of methods that we use to define times of sediment deposition, which is on the one hand, cosmogenic burial dating, and also uranium lead dating of circons in volcanic ashes. So the chronology I'm going to show you in this very schematic cross-section. In the Toro Basin, we find at least 6 terrace levels. On the one side, on the other side, there's 4 preserved, they're paired. And out of these 6 levels, we dated 3 of the surfaces, the T2, the T4, and the T6 level. And at each of these levels, we have cosmogenic depth profiles. And we can see that the uppermost terrace, the T6 one, was abandoned at about 450 to 490,000 years. The T2 terrace at about 260 to 285,000 years. And the T2 terrace sometime between 75 and 110,000 years. And then we add the dates of sediment deposition or times of channel aggradation. In the red stars correspond to the cosmogenic burial samples, and the white stars to volcanic ash samples that are incorporated into the fill. Now we can see that those ages fall in between those terrace ages, which already indicates that we must have had several phases of river aggradation and river incision. And this might become a bit more obvious when we actually look at the evolution of river elevation through time. So the horizontal lines that you can see here represent the different terrace surfaces. The black ones are those that we dated. And we know every time a terrace surface gets abandoned, this must have been followed by a phase of river incision, indicated by those down-pointing blue arrows. And then the stars represent the times of sediment deposition or aggradation, indicated by those up-pointing red arrows. And if we now connect all those arrows, some kind of cyclicity becomes apparent. And it looks like that about every 100,000 years, one terrace was formed, at least for the last 500,000 years. Okay, so it seems like these terraces have been formed in phase with some global climate cycles, but still, as I said before, changes in riverbed elevation can be formed or can be caused either by upstream perturbations in sediment or water supply, or by downstream changes in the base level. But for the Toro Basin, we think we can rule out the base level case, because the base level for the site where the terraces are is located by, or is controlled by a normal fold that is located a little bit further downstream. And it's very unlikely that this normal fold changed its rate on some kind of 100 kiloyear cyclicity. So we think it's very likely that these terraces were formed due to changes in upstream water discharge or sediment supply, or both. And as a first step, we're going to compare now our terrace ages to a paleoclimate record. And the only paleoclimate record that actually dates back far enough is the record from Lake Titicaca. So here we again have the curve of the calcium carbonate concentration, and those yellow vertical bars indicate the wet phases on the Altiplano Plateau when concentrations in calcium carbonate are high. In the second column, we have a global paleoclimate record. This time it's the benthic oxygen isotope record from the Atlantic and the Pacific. And we can see again that the dry phases on the Altiplano correspond to global interglacial phases, and the wet phases on the Altiplano correspond to global glacial phases. And here, this lower peak is the LGM. So then down here, we have now our terraces. Just for reference, again, the Toro Basin where the terraces are is located here. And in the third panel, we now see a stacked PDF of the terrace surface ages. So the times of onset of river incision for the T2, the T4, and the T6 terrace. And we can see that all of these peaks fall into the white spaces in between. So the onset of river incision seems to correspond to wetter phases on the Altiplano and globally glacial phases. On the lower panel, we see the PDF of the depositional ages. So the yellow ones are the volcanic ashes, and the red curves correspond to the cosmogenic depth, cosmogenic burial samples, although they have very high error bars. But all of the peaks, so the most likely ages of all of our depositional samples, fall into these yellow boxes, so they correspond to the dry phases. Overall, it looks like in the Toro Basin, we have sediment deposition during the drier phases and river incision during the wetter phases. So this is good. We now have the terrace chronology, but the question is now, can we use those terraces for some quantitative reconstruction of the hydrological conditions of the past? And for this, I'm going to return to this relationship that I was talking about before, that the slope of the river, the channel gradient, is a function of upstream sediment supply and upstream water discharge. And the idea here is that it should be possible to reconstruct water discharge of the past if we know sediment supply of the past and the channel slope of the past. So that the channel slope is probably the easiest part, because this is preserved in the terrace surfaces and we can just extract this from topographic data. Reconstructing past sediment supply is a bit more complicated, but we can get estimations of past sediment supply from the chemical composition of the terrace sediments, in particular from the 10 beryllium concentration of those terrace sediments that give us information on past erosion rates. And once we have information of past sediment supply, we can then calculate past water discharge. So I'll start off by talking about past sediment supply. And for that, we first take a look, in order to calculate past erosion rates, we first take a look at the distribution of modern erosion rates. And for that, we went into several places along the main stem and at the outlet of tributaries in the Toro Basin, everywhere where we have a little circle here. And we measured the modern erosion rates as they are preserved in modern river sediments using 10 beryllium, so cosmogenic nuclides. Just for reference, the terraces that I was talking about are located here within this black box in the center of the basin. And when we calculate those erosion rates, which are shown here by the different colors, we have a quite strong, spatial gradient. So in the southeastern part, where we have these dark red colors, this is where we find the highest erosion rates, and they are higher than 1 millimeter per year, on the order of 1.3 millimeters per year. But the further we move to the north and to the northwest, the lower the erosion rates get, and the lowest rates we find here in the northwestern corner on the order of 0.01 millimeters per year. And these rates are again summarized here. So the upper panel just shows the figure I showed you before, the evolution of river elevation through time. And this central panel here now shows the erosion rates through time. So all the data points that we can see here are just the modern erosion rates that corresponds to all of these data points here. And now, as a next step, we can go to the terraces and extract or reconstruct past erosion rates from those terrace sediments. And they are now indicated here. The different colors just correspond to different terraces. So the blue ones are those along the main stem, and the yellow and orange ones are terraces at the outlet of tributaries. And we can see that past erosion rates, as reconstructed from the terraces, are quite low compared to the modern spread that we see in the Toro Basin. And because they are so low, I'm going to zoom in a little bit more. So this lower panel now here is just a zoom in of this gray shaded area. And we can see that past erosion rates, they vary a little bit, somewhere between 0.03 and 0.05 millimeters per year. But yeah, if you, for example, just look at the main river terraces, we see that the erosion rates have been extremely constant through time, at least for those moments in time that we can reconstruct. Okay, so now that we know past erosion rates, we can estimate past sediment supply. And we could go to the next step and try to estimate past water discharge. But in order to do the full quantification, we need to take a look at the entire equation and not just at the scaling relationship. And the equation that I'm going to use is an equation that has been derived by Andy Wickett and published together with Taylor Shilkin. And it shows that water discharge is a function of the ratio between sediment supply and channel slope to some power. But there's also a couple of other factors in there. The intermittency, which gives us the time of geomorphically effective flow conditions, and some sediment discharge coefficient. So unfortunately, we don't know these parameters for the past. And our way to get around this is by using modern data for calibration to estimate those parameters. So I'm going to use modern water discharge, modern sediment supply derived from modern erosion rates, and modern channel slopes in order to estimate those numbers. And modern water discharge can be estimated from a gauging station. The gauging station is located here at the outlet of the Toro Basin, where the yellow stars. And at this site, water discharge has been measured between 1944 and 1961. So from this discharge time series, I just calculate a mean value, and then I scale it to each location in the Toro Basin based on the modern distribution of rainfall. So as an example, if this basin receives 5% of the total rainfall falling over the Toro Basin, I assume that the discharge at the outlet of this basin is equivalent to 5% of the total discharge. So this way, I have an estimate of water discharge for each site in the Toro Basin. And I can combine this with my data set from modern erosion rates and estimate modern sediment supply. And I can also measure the modern channel slope from topographic data. And then I get this modern calibration where I have the ratio between sediment supply and slope on the x-axis and water discharge on the y-axis. The linear regression doesn't look linear because the x-axis here is shown in log space. So if we fit a linear model to our data, we get an R-square value of about 0.93, which indicates that the linear model is a fairly good representation or fairly good model to describe the data. And from the slope of this fit, we can then estimate these parameters that we didn't know, K, QS, and I. So now that we have this calibration, we can do the next step and use the ratio from this from the terraces. So from the terraces, we reconstruct paleo sediment supply and paleo slope, and we can just see where they plot on along the x-axis and basically just read off water discharge of the past. And the interesting question is now, how does water discharge of the past compares to water discharge of today? And this is shown here as a plot showing past water discharge on the y-axis against modern water discharge on the x-axis. And the dashed line here is the one-to-one line. And all 4 data points for which we could reconstruct past water discharge indicate that in the past, when those terraces have been abandoned, water discharge was higher between 12 and 86%. So overall, our observation matches theory, because today we know we're in an interglacial phase. The region is extremely dry. We observe aggradation, while in the past, when those terraces have been abandoned, it seems like it has been wetter, and wetter conditions should cause a lower slope and therefore river incision. So as the last point, I would like to now compare these quantitative paleohydrological calculations to other quantitative paleohydrological records for the Central Andes. So what we're gonna look at is, again, the regional paleoclimate record from the Lake Titicaca. The yellow bars are, again, the dry phases, and the global paleoclimate record from benthic oxygen isotopes. And down here, we're going to look at a compilation of all available quantitative paleohydrological reconstructions from the Central Andes, shown over latitude and time. So the 4 data points from the terraces are indicated here by these 4 squares. So the squares represent the terraces, and the color of the samples gives the percentage by which it has been wetter in the past compared to today. From the terraces, we reconstructed that it had been between 12 and 80% wetter, so we're in this blue phase here. If I now add all the other available paleo records, we can see 2 things. So first of all, the amount by which it has been wetter that we reconstructed from the terraces corresponds quite nicely to other quantitative paleohydrological reconstructions from the same latitude. But compared to all the other reconstructions that are based either on the extent of lakes or glaciers or combination of both, the terraces, they date way further back in time. And with this, I would like to conclude. And I hope I could show you that the rainfall in the southern central Andes is to a large degree controlled by the monsoon system and the modern topography. From paleoclimate records, we know that the monsoon intensity has been varying through time, and changes in climate do impact river profiles, sediment transport, and the sediment transport processes in rivers. And therefore, alluvial rivers or alluvial river terraces are quite valuable archives of past environmental conditions, and they have the potential to date further back in time than the existing records, particularly lakes and glaciers. And with this, I would like to thank you for your attention, and I'm happy to take questions.
Excellent talk, Steffi. Thank you. So we'll give everybody here a minute to type in your questions. I do have a quick one while waiting for those. So given basically the power that your terrace records hold and basically going back in time, right? And that it's a quite arid place, do you tend to find a lot of calcic horizons or soils at all within your terraces? And kind of a follow-up question is, has anybody tried to look at kind of the moisture record with isotopes for that?
So in the terraces themselves, not really. So the terrace sediments are still quite loose. They haven't really been calcified much. There is some other regions where, a little bit further to the south, where soil carbonates have developed in like little rhizomes, and people have measured this, but not in the terraces themselves. So what I try to do, I try to extract organic material from those terrace sediments to measure isotopic composition on biomarkers. And the concentrations are just so low, or there's basically nothing in there, that, yeah, this didn't work out.
Oh, that's a shame, but I don't know. Here's the hoping, at least, right?
Yes. Yeah, I think the promising records, like longer term records, also are the lakes, because the lakes preserve more or less continuous records, but they are all located on the Puna Plateau today. So we are restricted to the high elevation area. And yeah, we are very limited in records in these intermontane basins and the foreland area.
Let's see. There are, let's see, no questions yet in the chat. So I do have another one. I love a good terrace. So I know that you just looked at the one basin, the Toro Basin. Do you find that there's other basins nearby, or potentially at slightly different latitudes, that maybe you could, or you or your team could basically target in the future to get kind of the latitudinal variation in time? I mean, it's a lot of work, obviously, but.
Yeah, so overall, these terraces are quite abundant in several intermontane basins on the eastern side, but also on the western side of the Andes. So we are not limited in terraces, let's say. And there has been more work on terraces. So my PhD supervisor, Taylor Shilkin, she actually did start working on terraces before I did. And she was working in the Humahuaca Basin, so the one basin further to the north, and has dated the terraces there. And the interesting part here is that those terraces are a lot younger, and that they are more or less in phase, not with the eccentricity cycle as those in Toro, but with a precessional cycle. So they are following like this 20 kiloyear cyclicity. Same, we find terraces in the Western Andes that seem to follow the 20 kiloyear precessional cycle. Then on the other hand, even for, like a region further north of that, there's a record that has been presented several times at conferences, is not entirely published yet, I think, where they didn't look at terraces, but at sediment depositions in the foreland. And they find some 400 kiloyear cyclicity in there. So we were asking, how is it possible that the same, or that regions that are so closely located preserve so different cyclicities, let's say. And our observation, at least, is that the larger the drainage basin, the higher the cyclicity that is preserved. And this, it just might be related to how far the information of changing climates basically travel downstream in a river system. So when the water discharge increases and the river starts to incise, it incises at the upstream end, and this information propagates downstream, but this takes time. So only the really long climate cycles heavily impact regions further downstream in the river, while short climate cycles also impact regions higher upstream in the river system. So we at least hypothesize for the moment that depending on the size of the drainage basin or the distance downstream, this is one factor that controls what kind of cyclicity or what kind of landscape features are preserved, the age of those. So yes, there are more terraces. There's also more projects in progress that work on those. But as you said, it takes a lot of time to get good chronology for such terraces.
Wow, that work sounds fascinating that you guys are working on. The idea of kind of this threshold for the kind of the time range or the capacity of the time range that you could record is very intriguing. I look forward to reading about that. Oh, I see one question in the chat here from Toby. Toby, would you like to ask your question?
Sure, yeah.
Okay.
I was just a bit sort of curious about what the geology of the terraces looked like and whether there was anything distinct about these ones compared to terraces around the rest of the world?
So with geology, you just mean the
Sort of
material?
like the cross section of them, and yeah.
Yeah, so those are all alluvial terraces, so they are not made of bedrock. So the material itself is just river sediments. And yeah, maybe you remember this one photo. It's just rounded glass that are coming from a little bit further upstream that have been deposited in between. We sometimes find some volcanic ashes when there has been some volcanic eruption, but overall it's all fairly soft sediments. And yeah, with the cross section, so the interesting part is that these terraces are paired. So they are, yeah, more or less at the same elevation on both sides of the river. Of course, not always preserved at all sites, but especially the middle one, the T4, can be traced along about 20 kilometers. So it's quite obvious. I'm not sure if this is exactly what you were after when you ask about the geology. And it seems like he's frozen now, at least for me. Oh, no. Did this answer your question, Toby?
I think that's a yes. I think I saw him nodding.
Okay.
Oh,
Okay.
sorry, my Wi-Fi's a bit unstable.
So I have another question kind of inspired by this. So considering that they're all alluvial terraces, did you find any evidence for how deep the bedrock is beneath your alluvial terraces? Like, have any of these rivers reached bedrock yet?
So this is not work from me, but work by Bodo Buchhagen. And what they have done is they have done some seismic investigations. And from the seismic data, we know that further down in the basin, where the whole basin gets very narrow and there's like this bedrock gorge, actually the region where this picture is taken that you can still see. Here we have about 10 to 20 meters of sediment before we reach bedrock. But further up in the basin where we have the terraces, it's another 120 up to 200 meters before we reach bedrock. So it's yeah, no, up there we haven't reached bedrock and we're not even close to it. So it's a lot of sediment. And the idea is also related to the work from Heiko Pingel, that this aridification that he observed in the isotope data, which was related to the uplift of the eastern range, that this aridification actually caused initially the filling of the basin with all the sediments, because the region kind of suddenly became very dry and there wasn't enough water available to bring all those sediments out. And then over time, so superimposed on this overall aridification, we have these climate cycles that cause some changes in riverbed elevation through time.
Okay, thanks. Well, I think that's enough questions for you today. And so again, I want to thank you very much for your wonderful talk about the South American monsoon. So I'll put our hands together for Dr. Stefanie Tofelde here.
Yeah, thank you very much.
You're welcome. And so next week, we do not have a speaker lined up for next week, but please keep a check on your email for announcements from all of us related to the next speakers coming in the lineup. With that, I hope everybody has a good morning, good afternoon, and a good evening. Thank you.